Hi there. Thank you. Quick, who am I? Why am I talking to you? What is the story here? My name is Craig. As was said, I work for Google Cloud, running the tools that you use on Google Cloud to build machine learning. Previous to that, I built and launched AWS SageMaker, the tools that you use to build machine learning at AWS. Fundamentally, I came into this space as a business analyst who wrote better SQL than most other people. And at some point, my boss said, "Hey, you're doing a really great job creating these insights. Could you make better ones?" And I kind of looked around and thought, no, but I could hire myself an econometrician. And so I hired an econometrician to start doing a whole bunch of cool logistic regression and what have you. And very quickly, they were asking me for better, could you get us better insights? Again, despite the fact that I was already delivering kind of 10x what I had been delivering previously. And so I started hiring machine learning scientists and kind of deep learning scientists. And for the first time, I had met a group of people that relished in their slowness. Right? I would turn to these machine learning scientists and they would kind of, a week into the project, I would say, "Hey, how are things going? How close to completion are we?" And they would say, "Well, we've got some good descriptive statistics." And so I got into this business of just constantly asking them, "Hey, what was the long pole?" And every time they would tell me what the long pole of the problem was, I would grab a team and we would go automate that. And then we'd come back and try and start over. And so today I want to talk about 3 of the things that I think are the long poles to us doing machine learning at kind of much broader, much bigger scale. We called this bigger, stronger, faster. But I think fundamentally the bigger, stronger, faster promise has already been delivered by cloud machine learning. Fundamentally, I can already process a petabyte of your data in a couple of hours across GPUs and all of these kinds of things. I can distribute a couple hundred GPUs to kind of quickly and easily train your models. So to me, that's actually, that one's a given. We've finished that. There are other opportunities now for us to kind of truly revolutionize this. The first one on bigger is explainability. Today, I have a hypothesis that the place where we're not using machine learning is where we don't trust it. Right? We don't want an opaque box telling us what was going on here. And when all we had was linear regression, it was easy. We could look at the model weights and say, "Hey, this is why it made this decision." But with neural networks and RNNs and DNNs and all of this kind of things, we've lost that capability. But the good news is we're coming back to the ability to find that capability again. We'll talk a little bit about that. The next one is AutoML. I have AutoML tables there about AutoML. Fundamentally, this is the ability for any of us to build a machine learning model that is on par with the best data scientists in the world. And then lastly, pipelines. So the ability for us to make components. Instead of asking our data scientists to become computer scientists and do the things they're not good at, what if we could just make those needs and efforts into components that they could use like Legos or what have you, right? So this is a bit of what we're going to talk about. Explainability, we'll start here. So this is a human retina. A couple of years ago, Google did a bunch of work to help improve the diagnosis ability of diabetic retinopathy, the leading cause of blindness in men ages, 25 to 64 or something like that, right? We rolled it out. We said, "Hey, look, we can predict the early onsets of this better than anyone else in the world." And doctors were against it. Doctors didn't appreciate it. They didn't understand why we were making the recommendations. They couldn't turn to all of a sudden, the doctor would say, "Hey, I've got this computer model that says you're not healthy, but I can't tell you why." Right? And fundamentally, it was as easy as circling the lesions. Right? All we had to do to fix this was tell doctors, "See that? That's why. Those little lesions there, those are why we're saying this." And now all of a sudden doctors could say, "Oh, right." Doctors are now getting better at it because they're seeing these lesions get highlighted. Right? We now have a better feedback cycle because they can tell us, "Hey, this is a lesion you missed." And fundamentally, they can turn to customers and say, "Listen, you are not as healthy as we'd like you to be, and this is why. We know why. We can show you why. You understand why." This, diabetic retinopathy, while cool, is probably not something most of us are dealing with every day. Most of us are probably dealing with massive data warehouses of data. So what if a model could kind of descriptively tell us what the most important features were? Or what are the columns of that model that are the ones dictating the decisions this model is making, right? Summarized for the whole model, saying, basically that, hey, marital status, never been married, is going to be kind of a key feature, or that's going to be the reason why this model makes its decision more often than not, right? What if we could do that not only for the model, but also for every single inference, right? So every single time you ask the model for an answer, the model told you not only what the answer is, but why the model thought that was the answer, right? By the way, this is a cool thing that now we're just starting to be able to do kind of at scale within machine learning. My guess is this is something that will become legislated in the fullness of time, right? Is that you won't be allowed to have a model that you don't understand anymore, right? And so giving those tools at massive scale is kind of critical to this space. And then doing it with unstructured data. This is the cool one to me, just because I'm a geek, and this is the geeky one. The picture with all the little green dots, those are the pixels as to why the model chose to say that this is an ape or a chimpanzee, a baboon, I guess, right? Baboon. So, those are the specific pixels that made that decision. You can imagine that if we made the wrong decision, right? We said, hey, this is a dog. We could very clearly now look at the pixels that made that distinction and correct for those very easily in the model moving forward, right? So, all of a sudden, we have the ability to understand these kind of, massively complex models. I'll also say that any excuse to use the words collisional game theory is like anything that uses collisional game theory, I'm just kind of naturally interested in. But, the ability for us to do this at scale for basically any model type, I think gives us a whole new ability to have trust in these models and to be able to deploy them in ways we never would have imagined, right? To be able to deploy them on those things where we have traditionally said, yeah, we could do it, but I don't trust the model here, because now we can understand at least why the model is doing what it's doing. So the next big piece, the stronger piece, is AutoML. AutoML is fundamentally the ability to build a model with very little knowledge of data science, right? So, fundamentally what we do is we start here with your data. You kind of tell us what your data is. In this case, it would be a table. You tell us a little bit about, hey, this column is a number, this column is a string. You tell us relatively basic things. And then all the hard parts that we count on our machine learning scientists to do. The algorithm selection, the feature engineering, the hyperparameter tuning, all of that, the computer takes care of, right? And I mean, I'll say this is kind of the cutting edge technology to be able to do this. We've recently launched some products in vision that do this, in natural language that do this, and now in structured data that do this. And what we're finding is that people are using this for use cases because the cost of entry is so low. I'm no longer, if I think about a machine learning scientist who makes a lot of money, let's say $200,000 a year for a machine learning scientist, and I get, 10 models a year, if I'm lucky, right? So, $20,000 a model versus 16, maybe $20, maybe 40 if you want to run it for a long time. The ability to iterate and experiment on different things completely changes in this paradigm. One of the critical pieces of this is what we call architecture search or algorithm search. This is basically, my guess is that this room would answer this question better than most rooms, but the question of what is the difference between stochastic gradient descent and gradient boosted trees. This is not a knowledge most people walk around with in their head. It's critical to making decisions about what kind of machine learning model to create, and there's no reason why a computer can't do that instead. And so that's what we're doing here. Fundamentally, it's not brute force, but it's trying a lot of combinations, right? It's training the model hundreds, if not thousands of times across different architectures to find the right one. Give an example of this. So Fox Sports in Australia was using this to predict wicket falls, which, for those of you who aren't big cricket fans, I would say that this is akin to when someone gets out in baseball, but those who are cricket fans will stone me for saying that. But fundamentally, it's something along those lines. And they got to a point using this technology where they could predict these with a relatively high degree of certainty about 5 minutes before they were going to happen. Which, I have to tell you, I think the data scientist at Fox, or I should say the customer at Fox, I don't know that it was a data scientist, made a huge mistake in marketing this and not just taking it to Vegas. But here they are predicting these wicket falls minutes in advance, right? And getting customers engaged at a level that customers were never engaged before with this, right? All of a sudden, a business analyst or someone who understands kind of the data scheme, hey, what data do we have? Someone who can understand that question is now building a model where they're predicting something that's driving a 50% use, up, or a 40% uptick in engagement and a 50% uptick in spending. Right? I mean, I can't imagine that we all wouldn't sign up for that, right? I mean, and the opportunities are there, and they're there beyond the use cases that we can think of. I was just talking before it came on. My belief is that machine learning is like this much about the complication of the tech and about this much about the change management that needs to take place in the organization to drive the organization to think, every team or every group thinking about how is it that I'm deploying machine learning in an effort to try and improve my business. That's a question that I've forced teams to answer in the past of kind of, what is your ML strategy, right? It's a good one to ask because very quickly you find everybody has an ML strategy when you ask that question. In the last, about a month ago, we hosted an event for a company that is part of Google called Kaggle. Kaggle, for those of you who don't know, is a machine learning, is a site where machine learning scientists get together to compete against each other on machine learning problems and to learn from each other and share code and discuss the newest technologies and things like this. We brought 300 of the best Kagglers from around the world. By the way, there's about 2 million Kagglers, people competing on this website for contests. Often the prizes are upwards of $1 million prizes for the person who can get the best model for this data set. So we brought about 300 of the best Kagglers together for a couple of days. And on the last day, we had a competition, one of their kind of classic competitions, and the AutoML entered as a participant. And what was funny was watching all these teams are huddled around these tables, pounding on keyboards. The AutoML team kind of came over, hit enter, and went and got lunch while things ran. And they came back about an hour later, and they were first on the leaderboard. And they were first on the leaderboard for almost the entire day. And I showed up about 6 hours into the 8-hour competition and was, I wasn't pleased. We had a lot of world-class data scientists in the room, and this wasn't my plan of how they would learn about AutoML. It was less than exciting. But so with a couple hours left in the day, a couple of the kind of grandmasters or key leaders in this community came together and built a model that beat AutoML, luckily. I was pleased about that. But then the actual magic happened, which is we got back to the office, and we took that human model. You can see the Urquhart and Mark model, and we ensembled it with the AutoML model. And what Ensemble does is you can think of it as average the two models out. And often when you have two teams approach a modeling problem, and they approach it differently, and you average it out, often you'll get a better result than either team's individual model. So we ensembled these models, we averaged them out, and you can see here we got a score that, while it looks not higher because these numbers are all in decimals, I mean, you can see the 6.18, thousandths better. But you look at how closely connected all of the rest of the top 10 are, and this top model is much better than the others. And so what this means is that the humans solved the problem one way. The humans used a bunch of intuition around, hey, if this is what I'm trying to predict, what would help me predict this from this data set? The computer used an entirely different method of kind of saying, hey, of all of the possible things I could do, which is the best one? They both came up with an answer, but when you combine them, you get a better answer, right? So they were solving this problem orthogonal to each other. And when you combine them, you get a better answer. And this is the excitement for me, is that, you'll see with explainability, it's not about taking humans out of this use case. AI will replace a number of jobs, but the goal of AI fundamentally is not to push humans out of the picture. It's to get humans working on the cool, important stuff, right? I mean, if I were to rewind the clock 300 years, most of us were in a field farming, right? We got tractors, and now we have massage therapists, right? Now we're getting AI, and I don't know what the next thing we're going to get is, but I'm pretty excited to find out. But so, bringing the human back in it's a critical part of this, right? Like, AI is not something we want running rampant. AI is something we want humans to be a part of. Finally, the last of these kind of three transformational technologies, the faster. This is going to be the geekiest one, which is a tough act at this point. I don't know how many of you have machine learning teams. I would assume most of you have machine learning teams, and I'm guessing that most everyone has lived this at some point, right? Where the data science team builds a model, takes them 3, 4, 5, 6 weeks, something like that. They come in, they say, hey, we've got this model that's 10x better than the way we're doing it today, right? Previously, I had done a forecasting problem where we took the forecast error rate from 5% to 0.5%, right? So massive change in the amount of wastage coming out of the system when we can predict that much better. And then it took us 6 months to get it deployed, right? So for 6 months, we had, we got 90% more wastage than we had to for 6 months. Like, that's millions of dollars, tens of millions of dollars, billions of dollars, depending on the scale. So fundamentally, we're building a technology called Kubbflow pipelines. Kubbflow, less interesting to memorize right now, but Kubbflow is an open source project that Google is working on, along with some exciting partners, IBM, Microsoft, Selden, a number of partners getting into this. Kubbflow is basically a Kubernetes-based system for building your own machine learning platform. But this pipelines piece is very critical. What this pipelines piece lets you do is it lets you kind of containerize or create these little pipes that have a very specific function. Hey, I'm going to have a pre-processing, or I'm going to have some transforms, or I'm going to have training or validation or analysis of the model skew and retraining. And I can now drag and drop these pieces, these defined functions, to build my model. Right? I have a 7-year-old who loves Scratch. And with a former MIT person on stage, I feel like it's okay that I assume you guys all know. Scratch is this visual-based programming language for kids where they just drag and drop these little bricks together. And every day when I come home from work, my son has some video game that he has made for me, which usually involves balloons flying at my head or something like that. But there's no reason why in a couple of years he's not doing the same thing with sophisticated machine learning capabilities in those little blocks. And so this allows us to think about speed and scale in a way we never have. Baker Hughes, so a GE company around energy and energy monitoring, uses this technology. And you can see here, they've got a tremendous amount of data coming in, right? So basically what they're doing is they're taking all of the sensors off of an oil rig, right? Tens of thousands of sensors on one of these oil rigs, all pumping data up. And they're trying to predict. They're doing a predictive maintenance game. The issue is that these things break so infrequently that you actually can't predict their breaking. What you have to do is you have to try and predict steady state and then watch for something that isn't steady state, right? And so, so they're predicting steady state of all this. Now, the steady state data coming off of these things is unbelievably tumultuous depending upon what's going on with the other sensors, right? The temperature changes outside, all of a sudden every sensor is reading something new, right? So what they ended up doing is they ended up using 10 plus architecture parameters, 100,000 model parameters. So 100,000 individual little knobs and dials that need to be tuned for a model, and 250,000 architectures. Right? So this is, you can think of that as 250,000 different versions of some sort of, RNN or DNN or some sort of neural network, all set up in different architectures. They're running through all of this constantly, right? 2,000 GPU hours, 7,000 CPU hours, and that's for one model. And they're running 100,000 of these models concurrently. Right? What they've kind of attributed it to, imagine trying to look at a city from an airplane and predict what's going to happen next in there, right? I mean, that's the level that we're doing, and we're able to do that because of the kind of, not only the compute capabilities, but because so much of this has been operationalized into these little chunks, it can now just be programmatically built instead of being hand-coded each time. So, unfortunately, we're running far enough behind that we don't have time for questions. I'll be around for a while. That's me. If you have questions, feel free to shoot me a note. I'm offended that no one's taking pictures of that slide. Come on. Yeah, thank you. But thank you guys very much for the time. I hope you're as excited about this as I am, and I look forward to working with any of you who are excited about it. Thank you.